Okay, let's take a look at the difference between acid strength and acid concentration. If I have an acid that's mostly dissociated, meaning it breaks into hydronium ions and anions, then I have a strong acid. And because I have mostly products, mostly ions, then what I have is a large Ka. If I have an acid that stays mostly as molecules and not much of it breaks apart into ions, then I have a weak acid, and when I have a weak acid, I have a small Ka. Remember, these Ks are just equilibrium constants. The subscript is reminding us that it's an acid equilibrium that we're looking at. If I have a strong acid, then it turns out that I have a weak conjugate base. If I have a weak acid, the converse is true. I have a strong conjugate base. In general, when I have strong acids, they're going to dissociate at 100%, so at equilibrium, my hydrogen ion concentration is going to be essentially equivalent to my original acid concentration. So the reaction goes way to the right. There's essentially no acid molecule left, and the concentration at equilibrium, again, of my hydrogen ion or my hydronium ion is essentially equal to my initial concentration of the acid itself. There are only 6 strong acids. We talked about these, a number of chapters ago. You need to know them. So see if you can remember what they are. We'll start listing them here. Strong acids, hydrochloric. We're staying with the halogens, so we have hydrobromic, hydroiodic. Then we look at polyatomics. We have nitric, sulfuric, and the final one is perchloric. You need to know these. These are the 6 strong acids. All other acids are weak acid. So make sure you've got this committed to memory somewhere along the line. Now, we have a problem with sulfuric acid because it's diprotic. Diprotic means 2 protons, so 2 hydrogen ions. Only the first hydrogen ion is a strong ion, will completely dissociate. That second hydrogen ion is less inclined to leave the sulfate ion. It's somewhat strong, but it's not 100% dissociative. So we have to deal with an equilibrium when we're looking at the hydrogen sulfate ion. So hydrogen sulfate ion is a weak acid, which means it's going to set up an equilibrium between the hydrogen ion or the hydronium ion it produces and the sulfate ion. Now, under some circumstances, under many circumstances, you can push it so it goes all the way to the sulfate ion, and we liberate both of those hydrogen ions. But in general, just the first hydrogen of the sulfuric acid is considered really strong, but that allows us to class sulfuric acid as a strong acid. Strong bases, again, we talked about what are the strong bases. You need to know them. They're the group 1 metal hydroxides. And in group 2, they are the bases below and including calcium. Now, the problem with the group 2 metal hydroxides is even though they are classed as strong bases, some of them are not very soluble. So when they dissolve 100%, but getting them as solids to dissolve in water is a solubility problem because of the lattice energy and less of a problem because of the intermolecular forces between the positive and negative charges preventing them from breaking apart, such as a weak base might experience. You need to know the strong bases just like you need to know the strong acid. Another term that we talk about when we're working with acids and bases is the term amphoterism. Amphi means essentially either way. Terism refers to the form. So an amphoteric substance can actually behave as an acid or a base depending on the situation. So if we look at this reaction on the left, we have water reacting with hydrogen chloride, and we get hydronium ions and chloride ions. So in this case, hydrogen chloride behaves as the acid, water behaves as the base. So we have a Bronsted-Lowry conjugate acid-base pair here. Hydronium becomes the conjugate acid, and chloride is the conjugate base. That's pretty straightforward. We've seen this reaction. If we look at this reaction on the right, we have water reacting with ammonia. And in this case, water is giving up its hydrogen to form the hydroxide ion. So when we have something giving up a hydrogen or donating a proton, it is assigned the term acid. Our ammonia molecule becomes the base because it's accepting that proton. We have the ammonium ion that's formed because it accepted the proton. It now becomes the conjugate acid. And our hydroxide is the result of a hydrogen ion being given up, and so this is our conjugate base. So here we have an example of water in one case behaving as a base. Here we have water in this other reaction on the right as water behaving as an acid. So that's an example of a compound that is amphoteric. It can behave as an acid or as a base depending on the reaction that it's in.